In this lecture, I'm going to be discussing the mean value theorem and some of its applications. So first we want to start with sort of a simplified version of the mean value theorem, which is called Rolle's theorem. So what Rolle's theorem says is that if we have a function f that satisfies these three hypotheses, then there's going to be at least one point c in an interval ab so that the derivative is equal to 0. So we'll go through these different hypotheses. So if our function is continuous on the closed interval ab, we've seen that there's some special properties that functions that are continuous on a closed interval have. If the function is also differentiable on the open interval, and we say differentiable on the open interval because we want to be able to talk about what's happening on either side of the point. So we won't talk about differentiability at the endpoints, but we'll say differentiable on this open interval from a to b. And if we also have the y values at the endpoints being equal to each other, then this means that there has to be a point in the interval where the derivative is 0. In other words, there has to be a point in the interval where the slope would be 0 or where we would have a horizontal tangent line. So there's a few different pictures that we can have in mind that express what this theorem is saying. One is that if we just have the simple case here where f of a and f of b are the same, and in fact everything's the same in between, then we would just have a horizontal line, and then at every point c in that interval I would have the derivative equal to 0 because this is just a horizontal line. But more generally, maybe I have something like this, where a and b are equal to each other, and I can connect these in various ways as long as I'm continuous, and I have the curve being smooth so it has no sharp corners so that it will be differentiable over that whole interval. So I could do something like this, have it just kind of go up and come back down to b, and again I have a place in between where I would have this horizontal tangent line. In other words, a place where the derivative would be equal to 0. And I could also have it do something a little bit more involved in between. As long as I'm going to start at A, be continuous, and end at B, I could do something like this, have it kind of go up and go back down and then come back up again. And now I see that in this example I would have multiple locations where the derivative would be equal to 0. So what this theorem says is that if we have these two conditions, then there'll be at least one value in the interval where I would have a derivative of 0. Okay, and if I don't have one of these conditions being met, or if I don't have this last condition being met, then this conclusion does not necessarily have to be true. And we sort of investigated how we can come up with examples that don't meet all the conditions of our theorem, and we can show how in those cases our conclusion doesn't have to be true. We could do the same thing here, but we're going to focus on applying this theorem in various situations. So here's an example where I have a function equal to sine of 2x, and it's on the closed interval from 0 to pi over 2. So I want to know, does Rolle's theorem apply to this function? So I want to think about the three different conditions of the theorem and determine whether the function meets those three different conditions. So the first condition had to do with whether the function was continuous. So is f continuous on the interval from 0 to pi halves? And so our function f of x is sine of 2x. And that function is defined on all real numbers. So it's continuous. So this is defined on all real numbers. And since our trig functions are continuous on their domain, its domain here is all real numbers. So continuous on all real numbers. So it's certainly continuous on this small interval from 0 to pi halves. So that's certainly true. Okay. So what about differentiability? Is f differentiable on the interval, the open interval from 0 to pi halves? So to think about whether it's differentiable, we'd want to think about the derivative. Now we have an idea that our trig functions are all differentiable, but sometimes we'll have to compute the derivative and kind of look at the domain of our derivative. So f prime of x here would be cosine of 2x times 2. So 2 cosine 2x is certainly defined for all x. Okay, so our function is differentiable on the interval from 0 to pi halves. So we have the first two conditions being met of Rolle's theorem. So what about the last condition? So we want to know, is the y value at our endpoints equal to each other? So we have to compute f of 0. So I see that sine of 0 is equal to 0, and f of pi halves is going to give me sine of 2 times pi halves. So I'm going to have sine of pi, and sine of pi is also 0. So these are in fact equal to each other. So the answer is yes, because I have 0 equals 0. So this means that Rolle's theorem applies. So I can answer this question and find the points where the derivative is equal to 0. So the theorem applies because these three conditions are met. So I have my derivative here. So we're going to set 2 cosine 2x equal to 0 and solve for the point that's in this interval where the derivative would be equal to 0. So I have cosine 2x equals 0. So I have to think what angle has a cosine of 0. So if I think about my unit circle here, I see that at pi halves I would have a cosine of 0. So that means 2x equals pi halves, which means x equals pi fourths, or in the notation here I could say c equals pi fourths, is the location where I would have my derivative equal to 0. Okay, so this is how we can work through an example like this. We also want to see how this looks with the picture of our function. So we'll go ahead and go to the next slide here. So this is a graph of sine 2x, and I was in particular interested in what was going on between 0 and pi halves. So 0 is here, and pi halves is here, because we showed that both f of 0 was 0 and f of pi halves was 0. And we found that f of pi fourths, f prime of pi fourths was equal to 0. So right around here where I get my horizontal tangent line, that is occurring at pi fourths. Okay, so I can see with this situation, I had to start at 0 and end at 0. I had to go up and come back down, and that agrees with the location where my theorem said that I would find this location where the derivative would be equal to 0. Okay, so we have examples like this where we can use the theorem to find certain locations where I would have a 0 derivative. We can also make use of this theorem in a different sort of context, but it turns out to be quite useful to solve problems that look something like this. So this is another situation where we can make use of this theorem. We're actually going to make use of two different theorems here. The first part is going to recall our intermediate value theorem. So in this next example, we want to be able to show that the equation 2x plus cosine x equals 0 has exactly one real root. So we remember doing some of these problems with showing something has a root by using the intermediate value theorem. So our first step here is going to be to show that 2x plus cosine x equals 0 has at least one real root. And then we're going to use our Rolle's theorem to show it has to have exactly one root. So we're going to show that it does in fact have a root, and then we're going to show that it can't have more than one. Okay, so if I want to show that this has at least one real root, remember that I could define my function to be what I have here on the left-hand side, 2x plus cosine x, and then I need to find some values a and b where f of a is less than 0 and f of b is greater than 0. So let's say that f of 0, that's an easy number to plug in, f of 0 gives me 0 plus cosine of 0, which is 1, and now I want to plug in something that's going to give me a value that's smaller than 0, so I'm going to try negative pi. So negative pi will give me negative 2 pi plus cosine of negative pi. That'll put me over here. Cosine of negative pi as well as cosine of pi would give me negative 1. So I have negative 2 pi minus 1. So we can see that f is continuous. Remember, the intermediate value theorem required continuity is continuous on the interval from negative pi to 0, since it's defined on all real numbers. So its domain is all real numbers, and this is a combination of just a polynomial and a trig function, so that's going to be continuous on its domain. So it's continuous on this closed interval. And we have f of negative pi is this negative 2 pi minus 1 is less than 0 is less than f of 0. So remember, this is one of our conditions of the intermediate value theorem. So by the IVT, intermediate value theorem, so we're using intermediate value theorem, there is a c in the interval from negative pi to 0 where our function is equal to 0. So there is a c in this interval, so that if I plugged c into this, I would get a true equation. 2c plus cosine of c would be equal to 0. Okay, but this problem is asking me to show that there's only one solution to this equation. So in other words, the equation has only one solution. Okay, and it's in the second step that we're going to make use of something that Rolle's theorem tells us. Okay, so we know that there's one root, or there's at least one root. We want to show that there's only one. Okay, so we know, let me just summarize this, we know there is at least one root from the intermediate value theorem, which is good practice for us to review that. Now, assume for the purposes of contradiction, we're going to say we want to show that there's exactly one. We know there's at least one. Let's say that there's two. So let's say there are two roots, A and B. Okay, so we're going to try to show that this leads us to something that's impossible. So if there are in fact two roots, then f of A would be 0 and f of B would be 0, because that's the definition of being the root. So I'm saying I want to show that this has only one solution. So I'm saying what happens if I assume there are actually two solutions, where the solutions are different to each other. So I have f of A is 0 and f of B is 0. Remember, that's one of our let's see what I want to say. One of our hypotheses of Rolle's theorem is that the y values at our two endpoints are equal to each other. Also note that our function f, our function here, f equals 2x plus cosine x, is continuous on an interval AB, since it's continuous everywhere, and it's also differentiable on AB. Okay, since it's just made up of this trig function, this other function, we know that f prime of x would be 2 minus sine x, and that function would be defined everywhere. So we have the three conditions of Rolle's theorem. We have our y values are equal to each other, we've got a continuous function on a closed interval, and we've got our function being differentiable on an open interval. So then the theorem says that, so let me say by Rolle's theorem, there is a c in the interval AB so that f prime of c equals 0. Okay, so let's see what that would mean. If there's a value where the derivative would be equal to 0, that means that 2 minus sine x would equal 0 for some x, which would mean that 2 is equal to sine x. So does that have a solution? Well, we know that our sine function is always just between -1 and 1, so that would have no solution. So this is what we call a contradiction. So we must have only one root. That's the end of our argument. So we were able to argue that from the intermediate value theorem, we know that this has a solution. And we said, okay, I want to show that there's only one. So let's just say for the case of argument that there are two different ones. What would that mean? Well, if there were two different ones, then Rolle's theorem would say that these two things would have to be equal. But since that's impossible, there must only be one root. Or in other words, we must have had A and B being equal to each other. Okay, so this is one of the interesting kinds of things that we can use Rolle's theorem to do. Okay, so now we want to just say a little bit about what the mean value theorem says and how it generalizes Rolle's theorem. So if we let f be a function that satisfies the following, in this case, two hypotheses. So the mean value theorem has the same first two hypotheses as Rolle's theorem. We need a continuous function on a closed interval and a differentiable function on the open interval. But now we do not require the y values to be equal to each other. So we're allowing something like, this, maybe my function does this, or maybe this is way up here and it does a few things in between, but somehow it's continuous and differentiable between these two different points. Okay. Then the theorem says that there has to be a point C, at least one, in the interval where the derivative at C is equal to the slope of the secant line over the interval. Okay. So this says that if you draw the secant line over the interval AB, if f is continuous and differentiable over that interval, then there has to be a point where the slope of the tangent line is equal to the slope of the secant line. And it helps to think about this geometrically. So if I have this graph of f, and this is A and this is B, and I draw a line here, a secant line from A to B, I can see that if I drew a line parallel to that, it would have the same slope, and I could find this value C here, where the slope of the tangent line would be the same as the slope of this secant line. Here, I could draw, a secant line between these 2 points, A and B. And then, let's see, let me get a eraser. Just want to make that a little bit finer line. So I have this here, and I see that I could have multiple points that would have multiple C's that would have the same slope. I can see here I would have something that has the same slope, here, 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 really close by, and also here. So there's multiple C's with same slope as the secant line. So this theorem guarantees that if we've got our function being continuous and differentiable, there'll be at least one value where the slope of the tangent line is equal to the slope of the secant line. There may be only one, but there could be multiple ones. So we want to work through a few examples to see how this is going to work. Okay, my pen got a little bit thicker than I wanted, so go back down there. Okay, so let's work through a few examples. So here we have f of x is equal to 1 minus x to the 2/3 on the interval from -1 to 1, and we want to know if the mean value theorem applies to this example or not. So I remember I need f to be continuous on this interval, so I have to check that, and I need to also check is f differentiable on the open interval. So when I consider continuity, I look at this function. I've got 1 minus x to the 2/3. The domain of that function would be all real numbers, because I'm going to square something here, and I can always take even the odd root of something. So yes, it's continuous, okay, since its domain is all real numbers and it's continuous on the domain. Okay, so what about differentiability? So to consider differentiability, I need to look at the derivative of this function. So f prime of x is equal to -2/3 x to the 2/3 minus 1, so that's to the -1/3. So we get -2 over 3x to the 1/3. So looking at this, I see that f prime of 0 doesn't exist because I have a 0 in the denominator. But since 0 is in this interval, f is not differentiable on the open interval from -1 to 1. So the mean value theorem does not apply here. Okay, it turns out that this graph here would look something like this, okay, where I've got -1 and 1 here. So I could draw a tangent line from -1 to 1. It would be a horizontal tangent line, but I would not have a horizontal tangent line at this value at 0 because I've got this sharp corner there. It's a place where the derivative doesn't exist, not a place where I would have a horizontal tangent. Okay, so one of our conditions fails and we see that the mean value theorem does not apply. So what about this example? We've got a function equal to the natural log x on the interval from 1 to 4. So we want to know, is f of x continuous on the interval from 1 to 4? Okay, well this is the natural log function. We know that the natural log function looks like this. Okay, and so the natural log function has a domain from 0 to infinity. So it's certainly continuous on 1 to 4. Yes, since the natural log x is continuous on the interval from 0 to infinity, so it's certainly continuous on this subset. So what about differentiability? Well, I need to look at the derivative. So the derivative of the natural log x we know is 1 over x. So is natural log x differentiable in this? Yes. So f is differentiable on the interval from 1 to 4, okay, since the derivative does exist. At all x in that interval. Okay, so those are the two conditions for my mean value theorem, so I can go ahead and find the points that are guaranteed to exist by the mean value theorem. So I can say that, let's see, the derivative is 1 over x, so f prime of x is 1 over x. So we need to solve f prime of c equals f of b minus f of c over, f of b minus f of a over b minus a, where a is 1 and b is 4. So what we're looking at is 1 over c, or 1 over x, if we want to use the derivative in terms of x, is equal to 4, let's see, not 4. F of 4 is going to be natural log of 4. So we're going to have natural log of 4 minus natural log of 1 over 4 minus 1. So let me give us a little bit more room here. So we're going to be solving this for x, and that will be the value that's guaranteed by our theorem. So remember, the natural log of 1 is 0, so we have 1 over x equals natural log 4 over 3. So we have x ln 4 equals 3, or x equals 3 over the natural log of 4. So that's the location that would be guaranteed to exist by this theorem. In terms of our picture, we know that the natural log of 1 is 0, so 1 would be here, 4 would be over here, so I could draw a line between those two, and then somewhere around here that I have my c, or my x, the way I labeled it here, where I would have the slope of that secant line being the same as the slope of the tangent line to this particular point. Okay, so I want to just look at one more example, and then we'll be talking more about applications of the mean value theorem in class. So here we've got a piecewise function, and we want to know whether the mean value theorem applies. So I first consider, is f continuous on the interval from 0 to 2? And since I have a piecewise function, I need to worry about what's happening near 1. So I see that f of 1 is 3. So notice that we're reviewing a few things from earlier sections within this. So this is good practice for us. Remember our definition of continuity. A function is continuous if the limit as x goes to a of f of x is equal to f of a. So I know that f of 1 is 3, and then to figure out whether it's continuous, I need to consider what's happening as I approach 1. So the limit as I approach 1 of f of x is going to equal the limit as x goes to 1 of x squared minus 1 over x minus 1. So if I use some factoring, I see this is going to be x minus 1 times x plus 1 over x minus 1. So I'm just going to be looking at the limit as x goes to 1 of x plus 1, which is equal to 2. So since these things are not equal, it's not continuous on this interval. So the mean value theorem, does not apply. So we can't guarantee that there will be a point that's equal to the slope of the secant line from this theorem. In this case, it does happen to be true because my graph is this line with a hole in it, where I have this other point that's being defined. So if I'm going from, let's see, from 0 to 2, okay, well, my secant line between those 2 points is actually the same as this line. It would be just the line x plus 1. So there would be multiple values here between 0 and 2 that would have the same slope because they lie on the line. But that just happens to be true for this case. It's not guaranteed by the theorem. Okay, so we'll talk a little bit more about mean value theorem in class, and let me know if you have any questions.